Good morning, Chem 20s. Our lesson today is going to be on solubility and equilibrium. Performing a reaction in solution can change the rate, the extent, and the type of the chemical reaction. If we look at the term solubility, solubility is the concentration of and this part is key, a saturated solution at a specific temperature. For instance, if we look at the idea of potassium chloride, if this is the solubility of potassium chloride, this statement means that 33 grams of potassium chloride can dissolve in 100 milliliters of water at 70 degrees Celsius. That is the maximum because this is saturated. Solubility is always a saturated value at a specific temperature. The temperature part is important, which means anytime we write a solubility, you must attach a temperature to your solubility. Well, let's take a look at this then for a second. And we have three definitions that go along with this. You should know them already from grade 8. However, let's look at them in order. So the first one is based on our definition, saturated. Saturated means no more solute will dissolve at that particular temperature. So let's look at the example of iced tea. If we had saturated iced tea, that means that if I take a glass of iced tea and I take one more crystal of iced tea powder and I drop it into my glass and I give it a stir, at that temperature, that crystal will not dissolve because we are already saturated. We have already dissolved the maximum amount of solute iced tea in that quantity of water at that temperature. Now, there is another scenario, and that is when you pour yourself a glass of iced tea and you taste it and it's weak iced tea. Weak iced tea or unsaturated would be where more solute could be dissolved at that particular temperature. So again, I have my glass of iced tea, I take a scoop of iced tea powder and I put it in and I give it a stir. All of it will dissolve. Unsaturated means I have room for more solute to be dissolved at that temperature. Now, there is a special third case, and that special third case is something called supersaturated. Supersaturated, first off, is an unstable solution. And this unstable solution has more solute dissolved in that particular amount of water than should be allowed at that temperature. Now, this is not something we can do with iced tea. Iced tea is stable. Iced tea will just fall out of solution. We can't dissolve more in the water than we should be allowed. However, there are substances where if I go and I grab a certain compound and I dissolve it in a temperature at 50 degrees, there's a maximum. However, if I heat the water up to, let's say, 70 degrees, I will be able to dissolve more of this solute. So I am going to max out. I am going to saturate this solution at 70 degrees Celsius. However, then I'm going to very slowly cool it down from 70 degrees back down to 50 degrees. What you will find is if you cool it slow enough, that extra solute that was able to dissolve at 70 degrees will stay dissolved at 50 degrees. So I actually have more solute dissolved at 50 than should be possible because I gently cooled it. But the reason this is unstable is anything could pull this extra solute out of solution. If I was to drop in a crystal of this same solute, or if I was to possibly just flick the outside of the container, out of thin air, you would see this extra solute fall out of solution, and I now would have solute at the bottom of my container. It is unstable because we have more solute slowly dissolved in than should be possible at that temperature. And so when we raise the temperature down very, very slowly, we kind of trick the solute into staying in solution. Well, there are some basic factors that affect solubility. And when we talk about this, it is very important to understand, are we talking about a solid dissolved in water, a liquid dissolved in water, or a gas dissolved in water, because they react differently. So when I increase the temperature of water and I dissolve more solid into it, we will notice that more solid will actually dissolve. So when I increase the temperature of the water, I can dissolve more sugar. I can dissolve more salt. Temp Solubility increases with increased temperature. Now, there is very little effect on a solid if I increase the pressure. So little that we're not even going to talk about it. Now, when we come to liquids, whether I increase the temperature or increase the pressure, liquids, in all honesty, don't really dissolve more or less based on an increase of temperature and pressure. There's not a noticeable difference. Now, if you look in your textbook on page 222, liquids actually is a little bit more complicated than that. They will reference and say, because water is polar, if you were to dissolve another polar substance into water, as the temperature would go up, the solubility would go up a little bit as well. But overall, when we look at polar, nonpolar, and just in general, we would say that in a liquid, raising temperature or raising pressure really has little effect. Now, gases are very different. I would say the gas is almost the opposite of a solid. When you increase the temperature of a gas, you actually decrease the solubility. So I like to think of this as take a soda. If I leave my soda on the counter compared to I put my soda in the refrigerator, if I leave my soda on the counter where it's warmer, you will notice that it will have less fizz because less carbon dioxide will stay dissolved in it. When I put it in the refrigerator, so I decrease the temperature, when you open up that soda, you're going to get that great, and that is that carbonation, that gas trapped in your liquid that is dissolved. There is more gas trapped in there when it's colder compared to when it's warmer. So it's the opposite of a solid. Again, when you increase the pressure in a gas, you will also increase the solubility. In all of these cases, when we talk about dissolving a solid, liquid, or gas into water, we are assuming that these substances do not actually react with water. Now, what I would like to do is I would like to look at a solubility curve. So I'm going to get my pen back here. Make sure I got them. Okay. And so this is my solubility curve. It represents temperatures and it shows their solubility. So what amount of mass of solute is dissolved in 100 milliliters of water at particular temperatures. So these are curves. You'll notice some goes up, some goes down. They seem to react differently. So my question to you is, what does each line represent? Well, this is their solubility maximums. So because it's their maximums, we would say that the line represents saturated solutions. So for KClO3, this is the maximum at each temperature of KCl3 we can dissolve in. Anything below that line, we would say is not at its maximum, so that would be unsaturated. And anything above the line, if it possibly could dissolve, would be supersaturated. What is the solubility of K2Cr2O7 at 50 degrees? So let's find 50 degrees. We're looking right here on the table. So we're going to go across 30 grams. Now we have to be careful. Every time we reference solubility, it's always the solute dissolved in 100 milliliters of water at a specific temperature. And our temperature is 50 degrees Celsius. So when I ask to talk about solubility, it's got to be what's the amount of solute in the quantity of water, 100 milliliters is what's standard, at what temperature? At what temperature does calcium chloride and sodium nitrate have the same solubility? So let's find calcium chloride. That's this guy. And sodium nitrate, well, it looks like they meet up right here. So the temperature that is looks like it's just a little bit higher than halfway. So it looks like it would be about sodium nitrate, calcium chloride. It looks like it would be about 26 degrees Celsius. And again, if you want to put one of these, that means approximately 26 degrees Celsius. As temperature increases, which compound decreases in solubility? So we're going to look for one that actually the solubility goes down. Well, we only have one of those. So that's going to be Ce2 bracket SO4 bracket 3. As temperature goes up, we actually lose solubility. And we'll notice that about approximately once it hits 40 degrees Celsius, the solubility actually doesn't change at all anymore. The temperature has no effect after 40 degrees Celsius. Okay, our last one, and I'm going to come and give us a little bit more paper room. If 135 grams of ammonium chloride dissolves in 300 milliliters of solution at 40 degrees Celsius, what is the solubility of NH4Cl? Okay, so we know 135 grams dissolves in 300 milliliters. So what we're trying to figure out is how much then is going to dissolve in 100 milliliters. Because remember, solubility is always amount of solute dissolved in 100 mils of solution. So there's a number of ways we can do this. We can cross multiply 135 times 100 divided by 300. Or if it's easy, we can look and go, okay, how do I turn this number into this one? Well, 300 divided by 3 is 100. So 135 divided by 3 is what? Again, cross multiply, look to see if there's some connection from these ratios. Either way is going to work. So I'm going to take my calculator, 135 times 100 divided by 300, and my solubility, therefore, is going to be 45 grams of ammonium chloride will dissolve in 100 milliliters of solution at 40 degrees Celsius. Reminder, you have to include the temperature because they are asking you for a solubility. Okay, nature of solute and solvent interactions. Solutes will dissolve better in some solvents than in others. The solubility of compounds is determined by the intermolecular bonds of the solute and the solvent it's dissolved in. So we dissolve lots of things in water, but you can dissolve in other items. You can dissolve in alcohol, and we'll do a lab in, or at least we'll show a demonstration of that in chemistry 30. Solvents that are polar are more able to dissolve polar solutes. That also means that substances that are solvents that are nonpolar actually can dissolve nonpolar solutes. So, an example of this would be grease. Grease is nonpolar, which means it will dissolve in gasoline, but it will not dissolve in water because water is a polar molecule. Remember, polar molecule meaning one side slightly positive, one side slightly negative. Well, a perfect example of this is I remember painting my outdoor fence about 10 years ago. And I was not very smart. I went out there and I was painting oil-based onto my fence first, and just to seal the wood. And I was painting oil-based, and I got white paint all over my hands. And I went inside and I went to wash my hands, and water wouldn't get it off. And I had nothing that could get off the oil based. It was stuck to my skin and I had to be somewhere. And so I remembered that, hey, oil based paint is non-polar. I need to use something non-polar. Didn't have turpentine, didn't have anything else. So unfortunately, I had to go out in the gas and I had to take my gas can for my lawnmower, and I had to pour gasoline into a bucket, and I had to wipe and wash my hands in gasoline to get off the oil-based paint. Unfortunately, that meant when I went to wash my hands to get off the gasoline, it was one of those, would not ever recommend this. However, I could not get the smell of gasoline off my hands for a good day, day and a half. But again, it showed non-polar dissolves non-polar. The example of polar dissolving in polar is ammonia, right? Cleaning supplies will dissolve in water. But if you took a cleaning supply, it certainly wouldn't dissolve in gasoline because gasoline is the opposite of ammonia. It's nonpolar compared to polar. So I think the saying we like to say is like dissolves in like. Now, water is referred to as a universal solvent, and you've heard me say that many times because it has the ability to dissolve in so many substances. So, I have here a picture as we zoom in sodium chloride, table salt dissolved in water. The reason water dissolves so many solutes is because of three reasons. One, it's a very small particle size, right? 18.02 grams per mole. It's two hydrogens, one oxygen. It's very small. Secondly, it's highly polar. It's got a high polarity. It's got a high discrepancy between the hydrogen and the oxygen. Therefore, that polarity plays through to all other polar substances. And last but not least, it's because of the hydrogen bonding. Well, when we dissolve something, a lot of people think, okay, I'm going to take, in this case, glucose, sugar. I'm going to take glucose and I'm going to dissolve it into water. And because it's a molecular compound by me, it doesn't break into ions, but it will change from solid to aqueous form. So we're going to see the particles when I stir disappear. So I take a scoop of sugar, I stir it in water, it disappears. It dissolves, we'll say. Okay. Now, and most people think, okay, the sugar will dissolve and that's all that happens. Well, that is actually false. While the solid sugar is dissolving into aqueous form, as soon as we get some aqueous sugar, there's an opposite process that's occurring at the same time. And that is some of your aqueous sugar will actually dissolve back into solid sugar, or I guess dissolve is the wrong word, crystallize back into solid sugar. And so people might go, how do I see this? Well, the problem with this is it's kind of small enough that you don't get to see many details, but there is a little bit that you can notice. So, most substances dissolve in a solvent like water to a certain extent, and then dissolving appears to stop. We would say that that's a saturated solution. When we've hit saturated, no more solute can dissolve into that solvent. If the solution is a closed system, so a closed system, again, is where no substance can enter or exit. So if I had a container of water and I dissolve sugar, there's a maximum amount of iced tea I can dissolve in there. For me to make it closed, I would have to put a lid on it. That means that we would not allow any water to evaporate if it was hot out or anything else to fall in. Then we would see that there would be some very constant observable properties. When we see these constant observable properties, because nothing's going to change in the solution because it is closed, we call that equilibrium. So let's take a look at this example. And I'm using salt instead of sugar. So I have a salt cube and I am dropping sodium chloride into water. When we put it into water, it is going to dissolve. Okay, and I am going to dissolve the maximum. I'm going to stir and stir and stir, and this is going to be saturated. If I put one more salt crystal in, it's not going to dissolve. So I have saturated my water solution. What I'm then going to do is I'm going to drop in more salt into my solution. And all of us would say, but Mr. Camp, it's not going to do anything because it is already saturated. So putting more salt crystals into this is going to have no effect. Now, I would agree that it would have no effect that I could honestly see right away. You'll notice I put a lid on this, so this was a closed system. So I had saturated this, so I have NaCl floating around here. It's completely saturated. I then dropped in more salt crystals. And what we'll notice is because it's saturated, you're not going to see anything else happen. If we have, and let's count them up here, it looks like we have 4, 8, 9 crystals dissolved in solution. So that is my saturated. No more crystals will dissolve. However, over time, what you're going to notice is that although more doesn't dissolve, you will notice that the salt has changed shape. And the reason it's changed shape is because this is called dynamic, right? We know that particles are always moving. particles have energy. Solids vibrate, liquids move around so they can roll past each other. And so although this is saturated and 9 particles is our maximum in solution, that doesn't mean it's always the same 9 particles in solution. So just because little Timmy particle up here in the top right-hand corner is dissolved in solution doesn't mean he's always going to be in solution, and more specifically, doesn't mean he's always going to be in the top right-hand corner. Because they have energy and they're moving because they're particles, yes, 9 is the maximum, but this particle could crystallize out and go back to solid if at the same moment another particle is dissolving and going into solution. So we will see that there's going to be an equilibrium. There is still the equality of 9 particles, but as one particle goes into solution, dissolves, another particle can come out of solution and crystallize. And so at any given moment, we're still going to have only 9 dissolved particles because that's saturated. However, that doesn't mean the same 9 particles are always in solution. Chloride can come out of solution and crystal out if another chloride particle dissolves in. Sodium can crystallize out if another sodium particle crystallizes in. And what you'll notice is eventually we get to a rate where the rate of crystallizing coming out of solution is exactly the same as the rate of dissolving going into solution. So this is a moving piece. We still are at equilibrium because we still have the maximum saturated number of ions in solution. However, this is moving. It's a moving system. So let's look at this in text form. Solute particles that are dissolved in solution begin to collide with undissolved solute particles. So my NaCl in solution, my 9 of them, start to bounce against the other solid sodium chloride crystals. This energy transfer is going to cause some of them to go into solution, some of them to come back out. At equilibrium, we will say there are no observable changes that we can see. I can't physically see ions dissolve in or dissolve out. Ions, remember, very, very tiny and minuscule. We say that at equilibrium, we have constant macroscopic properties. Macroscopic means, can I see it with my eyeballs? And we don't see any changes. But we do know that the rate of dissolving into solution will be equal to the rate of crystallization. Anytime we have 2 opposite forces that occur at the same time, we say that they have dynamic equilibrium. So rate of dissolving is equal to rate of crystallization. Rate of evaporation is equal to the rate of condensation. That is a dynamic equilibrium.